all turn your phones off. Sta ik nu in beeld? Welcome everyone at the Innovation Café, also for the people watching at home. For the people that are here for the first time, I think there's someone, you've been here before, right? Yeah, I was gonna say. Anyway, for the people who are here for the first time joining us, Innovation Café is a networking event where we basically share what Eindhoven has to offer in the fields of tech and design. Today we have a presentation by Cassio de Campos, and he's going to talk to us about perspectives for artificial intelligence. So without further ado, I want to invite Cassio up on the stage and take it away.
Thank you.
Thank you.
Thank you for the invitation. I struggled a bit to decide what we would talk about, and then I decided to go with quite a light talk. There will be a bit of advertisement of things that we do, but most of it is not directly related to our work there. So before we start, this is the first slide with a bit of an ad of our lab. So in the university at TU Eindhoven, we have 60 plus people working in different facets of AI. And then in the slide here, you see some keywords such as robustness, safety, trust, reliability, fairness. And working in AI in this case means new models, methods, algorithms. So trying to improve AI for industry, society, but not with a direct goal of a particular application. So we also work with many applications, but the ultimate goal here is, can we make AI move forward as AI? And before I continue, a very important slide, a disclaimer here, because the next few slides, there are going to be a few of my own opinions. And because of that, I would like to mention that some of them might be just approximately correct. And they may have been chosen just to convey a point. And it has my biased view there. So because of that, it's important to make this disclaimer. So if you are watching at home or here, we can debate them on these topics. But some of them might be a bit controversial. So I will start by this perspective. So what AI is, and what does this mean? And then I took a few of the sentences. Intelligence as demonstrated by machines. And then the thing that is recurrent on this is that you're going to see that intelligence keep appearing again and again to define AI. So it's like you're trying to define something by using the own word to define itself. The middle one you see on the ACM, the largest computing association in the world, is study of intelligence and its realization in computer systems. Again, intelligence there. It doesn't help so much to understand this idea of AI, and we keep saying, you know, there is AI everywhere, and we are moving forward with AI. So what we can do to move forward to understand better? Well, it's not a pure field. There are many things involved there. I have listed a few of them there. But what we could do is try to take a look at what people are, you know, doing in AI from the start when AI was coined as this name. And this is around the 50s. So quite some time ago. It's an account, quite incomplete, but just to give an idea where we are now and what happened in the past. So in the 50s, this was mostly in other fields, and the name AI appeared because of a meeting there, was coined, and then there was a boom after that with algorithms for playing games, new programming languages that were very related to the development of AI, and neural nets. Neural nets is what is behind deep learning now, and we hear a lot about this AI, and the part of the boom is related to deep learning. And this is on the 50s, so it's just to give you an idea that was 70 years ago that these models were already around. Not exactly as they are now, but the beginning of them was already at that point there. And backpropagation and other things on the 60s, like the first robots, Eliza, which is a conversational chatbot, and decision trees models in AI appeared already, very used now, but appeared in the 60s. So again, a lack a lag of 50, 60 years on this. And backpropagation is in bold because this is the main approach method to learn these models that we use in deep learning right now, the neural nets in particular. And then this kept evolving, and in the 70s, new ideas like transfer learning, which is used very much right now to learn with a domain and try to transport what was learned, the models to a different domain. And complexity came into mind at that point, and came what was called the AI winter, because people started talking about, oh, this is all too hard, and there are computational results that say you cannot solve, you cannot do what you plan to do. It's going to be very hard with computers to do that. And that was the first AI winter. So this is the first part, but the most interesting is this second slide, because it's closer to us. The thing continued, people didn't give up. And in the 80s, there you would already find things like convolutional neural nets, many other things, Bayesian networks, the MATLAB language. And convolutional neural networks is this AI approach that is very, very important to deal with images. And was already in the 80s there, but it was not booming as it is booming now. And the thing continued with improvements on playing games. Alice was already a very sophisticated chatbot, so we could talk with. Deepfakes, which is something that we hear right now and talk about, was already there also in the 80s. Internet was booming, and again, another type of neural nets that are very good for time series or text, LSTMs were appearing there. And computers won chess against Kasparov, right? It was a big thing when that happened in the 90s, Deep Blue. And we keep moving on this, and those models started to become bigger and deeper. So the neural nets became bigger and started to solve more and more problems. And then we have this key thing called GPUs there. And these are graphical units that before were used to do graphics in computers, and now it started to be exploited to do parallel computing massively. And then this became the big boom that we are now. So the neural nets and this deep learning becomes state of the art for many, many problems. And computers start beating humans in many games, right? But we are still like searching for beating humans in many other tasks. So we're beating some, we're losing some others, and we keep moving forward. But is this helping us really to define what is the AI and where we are going in AI? So I've tried to put a picture here that for me defines a bit AI in a good way. So you have this humanoid, this robot trying to paint, and if you can paint something, I think this is quite a better explanation of AI if you would give AI as an explanation. I made a bit of a joke there with a blurred face because privacy is such important. Maybe at some point it's going to be important also for AI to have the privacy. But this is still not helping so much, so let's get concrete, okay? Let's get concrete on this. So what people think AI is right now. So I divided in industry in general, beyond AI industry, and I would say that automation of procedures, which are a long time ago being used and done, and predictions, decision support are there, but now we are calling this AI, but they are already there. We are just using a different name now. Okay, the processes have changed a bit, models and algorithms are better, but it's not a fundamental difference, but now it's called AI. So you can already hear from my speech that I'm a bit critical of this. So deep learning, random forests is very important. Random forests are probably the type of AI approach most used yet in industry. And then the final commercial use, well, AI for many people is basically what we saw in movies, or at least for a long time. But anything that simplifies life nowadays starts to be called AI. And then we have many examples with Alexa Siri and attempts to self-drive cars and translators. And in the research community, that's quite interesting. We keep debating, and we don't know what AI is, and we keep debating about exactly what AI means. And then the question that I pose here for the scientific community is, are we doing a good job on helping defining this field? Is this really the helping us on moving forward with AI? And then maybe we should look to what we are now, really. What is the reality? Why AI is booming so much? And my biased viewpoint is because we managed to couple the improvement in hardware, so physical improvement, with improvement with algorithms. So this picture is about GPUs that I mentioned. And GPUs and these models that we are using right now, deep neural nets, deep learning, they go together very well. And then if you look on this graph, this is the amount of computing, how it has improved over time. The scale is logarithmic, which means that a line means exponential growth. And in this side, you have the amount of computing, and on that side, you have the prices, which are also going down in a linear scale in a logarithmic graph. I know it's a bit hard to see there on the graph, but the idea to convey is that computing power has increased a lot, and this changed a lot our AI and where we are going. That's a key point. So what AI is for many right now when we talk about AI. So if you look down there inside, for many, this is deep learning, deep neural nets, because they are showing impressive results in many fields. They are very modular, easy to adapt, so expert knowledge enters when you build your model, knowing the domain. You are an expert, and then you study the domain, and then you build the model to solve that type of problem. Hardware is fitting with the needs, so we never had so much computing power for all that. And part of the fact that this is so efficient is because these nets are sort of a circuit. Really on the sense of circuit of hardware. Computations propagate over the circuit. It doesn't have really a meaning in terms of a more contextual interpretation. It's really a circuit of computations, which makes many things efficient. Some parts are still hard, like to learn, you need more time, but many other computations become efficient because it's a circuit. There are some consequences of that. So AI research has grown extremely, and funding, and all related to AI. And then many people start talking about regulations. People talk about black box, that the AIs that we are using are too black box, so you don't understand what is there. I criticize a bit this because understanding this is related to, like how much you can explain something depends to whom you are trying to explain. So I can explain to you every single detail of these black box models in what it's doing. And then what the people say is, but I don't understand. Well, but you see that understanding has many levels. I also don't understand in a high level what is happening, but in the low level I do. So the level of abstraction is very important here, and what we want about understanding. So we have to really pay attention on this, understanding and improving models and what we want from the models. Regulations are coming, but I don't think they should hinder research. Quite dangerous there. And there is a big talk on ethics in AI, which I'm not going to dive into. But I suggest this talk, which is online, is the Gödel talk by Moshe Vardi, and he discusses on ethics in AI in an interesting perspective. You find on YouTube. So some consequences of this is that I work with trying to identify deepfakes, but I don't generate deepfakes. And I had never done really like generation of deepfakes. And then I did a simple try here because there was recently a TV show about deepfakes. And I built a deepfake with the face of our ministers there in under an hour. Okay, if you look to the whole video, you're going to see a bit of mistakes, but this was in under an hour. Without any particular knowledge on how the things are. I took a manual from internet, I used the internet tools, I downloaded, and I did that. And for sure you saw the Queen of England dancing over tables and Tom Cruise saying crazy stuff. But this is done even without knowledge of anything. Really, you don't need any intrinsic knowledge of what is going behind. So there are consequences, and some people are claiming, oh, this is dangerous. So for instance, why deepfake is good in any way. So the question that then I arrive here, which is the half of the talk, is what AI could be. So the current approaches will become better and better because, we have better computing power, and the approaches are so flexible that if you give more computing power, and they get better on what they are doing. But energy consumption is also increasing with that. So we are spending a lot of energy to do that. Some people are already even counting how much energy we are spending compared to what we are doing with those models. And the thing doesn't look that great for the future if we continue going in that direction. But I'm putting as a question here, not as necessarily a problem. These models we are using are really strong fitters, so they fit models very well. They are very good for particular tasks. But they have underlying issues, right? So there are examples that maybe you see on news. People manage to take an image and change one little pixel, so one little dot there, or a few of them, and the self-driving cars already go crazy with that. as you can see in many other examples. But this shows how dangerous it is. So there are underlying issues with the models that we are creating. So it becomes a concern to many, but we are still in that moment that the benefits are so great that we are maybe, we are starting to think about the concerns right now, I think, in society in general. And obviously, industry wants to exploit this as much as possible. There is nothing wrong with that. We also want as users. We just don't realize, but we are doing that all the time with everything that we are doing online. So many in the research community are starting to discuss and be concerned about that, and there is no even consensus about people talking a lot about explainability. And as I just discussed a few moments ago, you have to define to whom you are going to explain. This explainability is a vague thing. Black box is a vague thing. Everything can be black box if you don't understand anything about the topic. Many things in many fields for me are black box because I don't understand them, but are they really? So we have to really work on this explainability issue to improve, but even on defining what it means and working on that. And a more general, really artificial intelligence may still take time, in my opinion. We will see. But there are lots of developments that we should do in order to try to get there. So ideas on where to improve this. So I will show one idea. So my idea is very biased because it's an idea that we created, but in general, we want to improve the models, interpretability, efficiency, the quality of results, accuracy, without losing anything. And not always you can do that. Often you have to give something to get something else. That's the most common thing in the field. You want some kind of approach that is better on explainability, usually is worse in efficiency or accuracy of the results. And then we have to find this trade-off. Causality will play an important role. Causality is a part of our theoretical studies, causal models that is starting to be explored right now. It's really putting correlations apart, and this joke people talk about very often. There are many things that are correlated, but one does not cause the other. And many people are now starting to put correlations aside and really trying to find causal things. So this causes that, and not just these two are correlated, so they are associated in some sense. And as I mentioned, the level of abstractions is essential on all this, because depending to which level you are discussing or even implementing things, it changes what you do. Many properties don't come for free, and then the question is if we are really willing to pay this price. And it's a balance, because it costs to pay this. To be more explainable or to be more trustworthy, you pay something. So maybe you make less money. Maybe you have less accuracy. Maybe you save less patients. But when you do in a way that you can explain why. And this is very tricky. So there is a huge debate to come on that. Then this comes to my second part, where I'm going to tell about one special case where we took an AI approach, an AI model and algorithms, and we managed to improve it without losing anything. But that is very uncommon, and that's why I like this. So in the lab, we are trying to find, to work on AI that has principles. So you are, let's say, you can put all statistics on your back, on your side, and build models that have like many types of guarantees when you learn and when you do inferences. And we took one type of approach, called probabilistic circuits, and I'm not going to try to dive you into the details, but it's a sort of a circuit, and you can put this in a graph, and in the nodes of the graph, you do very simple computations. Either you do a sum, or you do a product, or you have a distribution over a variable of your domain. So you work with very simplistic models that do very simple computations, and you do computations over a big graph. And the graph looks like this, with nodes connected, and you propagate numbers over the graph. So I will not try to dive into what each thing means, but we managed with this type of graph under very mild properties to encode very complicated domains by using a probabilistic model. So everything that you compute there are true probabilities with all the properties that you have in statistics. And then what we did with those models. So we wanted to work with joint probability models over domains. It can be very many variables and examples. You can put many things on your problem. In this example here, is the same as saying that I have two variables and I'm treating two things in the example. For instance, it's sunny or not, and I'm using an umbrella or not. Those are variables, and then can be true, false, or they can be numbers, like what's the height of someone, what's the weight of someone, and then you put a probability over all the space of possibilities, and you try to do inference with that. So what we did in this work is that we took one model called decision trees, one of the most simplistic models in my opinion, but very well performing, used in industry all over the place. Decision trees are so simple that we can talk about there in a second and already understand what it means. So you have this graph, and then you have some variable. As I said, x2 could be some information about a person. And as you go in the model, you take a decision based on a sample that you want to, for instance, classify or know something about, predict something about that sample. And you go on the nodes taking decisions. In this example, if the value of x2 is less than 0.5, you go to the left. If it's greater than 0.5, you go to the right. And then you keep doing this until you get to a leaf, so to the end, and then you have a prediction there, which can be proportions, a probability, or something like that. This is a decision tree. What we managed in this work is that we extended the decision tree with a few more properties using the idea of probabilistic circuits that I just mentioned. And what happened with those models, by just putting some weights on the arcs and treating these in a very particular way, we figure out that decision trees are nothing but probabilistic circuits with a certain characteristic. So decision trees lacked a few properties which probabilistic circuits had, and because we can interpret decision trees as probabilistic circuits, we got all the properties for free by this interpretation and using them as probabilistic circuits. So this holds also for random forests. So maybe decision trees you don't use in practice. So if you are there, an AI practitioner, you say, I need a random forest, holds the same. So we can do the same for a random forest. And random forests are widely used. And now we have this probabilistic interpretation over this use of this model that before was not probabilistic. So all the guarantees and properties that you have with probabilistic model are coming for free on top of your random forests. I will give you two quick examples of things that we gained that we didn't have. So the first is outlier detection. Because it's a probabilistic model now, I can compute probabilities that I couldn't. So I can compute probability of a sample that you give me that you want to predict something. So you give me an example from the world, but you don't know, for instance, the class of this. And you want to predict this class, or you want to predict the value, how much it costs. You want to predict something. You don't know that, but you give me the sample. I can compute what is the chance of seeing a sample like that, because my model is probabilistic. When I do that, if this thing that you want to classify or find a property has high probability of being seen in the world, according to the model, then typically your model is better to predict because you saw it before many times, because it has a high probability of happening. So because of this probabilistic interpretation, we gain this kind of property. So what we can do now, and we did, was to look to the probability of samples, and we divided there in a data set. It's a very simplistic data set about wine, and you have red wine and white wine. In the left side, we trained our model, we created a random forest only with data from white wine, and we wanted to predict the quality of the wine. And then we create the model is very good, predicts the quality of white wine. Now we take to the model and show a sample of red wine. The model never saw red wine before. So what happens? I hope that the model tells that red wine has very low probability of existence because I never saw before. And that's what we see in practice. So in the graph there, which is the lower graph, the model can split based on the probability very well the type of wine, even wine that the model never saw. So all the red wines is going to say, oh, this is a very rare thing because it doesn't look like white wine. I never saw this before. Interpreting probabilities, it has very low probability. That's what the model can do now for us. And you can do this for outlier detection. So it's something you never saw, we compute the probability is very low, oh, this is an outlier because the probability is too low. And we did the same, repeating the other way around. We trained it with red and we got the same results by showing a white, and the model said, oh, this is something strange with very low probability I never saw before. The second example that I want to mention is treatment of missing values. So it's very often that you are working with data sets, but your data set has lots of holes in the middle. So your data is not complete. You don't have information for all the features of your samples when you are trying to predict something. Because it's probabilistic, we can do exact computations with the model of probabilities in the proper way by ignoring the missing parts that are inside. And typically with decision trees, random forests, you have to do some kind of tricky heuristic ways when you have missing values. And then we found results that are superior to state of the art. We compared it to a few different approaches. The 0 here means our baseline, which was an imputation by KNN, and the curves that are above means that are better than this baseline, and curves below are worse. And the two graphs on the far right are the ones of this new approach. So they are the top models on this. And then I did a last attempt, which is robust classification. So the model has probabilities, and I can even attack the model. Attack is that example that I told you, where somebody changes the data a little bit. I'm looking, that is the time, if somebody is worried why I keep looking there. You change the data a little bit, or the model, and you want to check if the model still predicts the same thing. And these formulas that are here, I will not even try to talk about them, but because of these characteristics of the model that we have, we are able to compute a sort of a robustness measure for the model that tells how much you can perturb the model, and the model still tells you the same. So you keep changing the model, and this robustness is how much you can change your model and it still tells the same result per instance, per thing that you try to do. And that's the result. So on top is the MNIST, very famous data set. Everybody tries to show things with that. And in the bottom is the fashion MNIST, also very famous data set. And the colors here, so on the left, you have the cases that we try to predict the type. So on top, we want to predict the number. And in green is the ones that we got right. In red is the ones that we got wrong. And the left are the cases that the model told, I'm not very sure. So the robustness measure said, if you perturb the model, you might make mistakes. So we already knew those were complicated cases. And on the right, you have the cases that the model said, I'm very sure of what I'm doing. So you can even perturb the model, and I will keep saying the same. So for the, say, top right case is a number 7, and the model said 7, you perturb the model a lot and it still says 7. So the model was very confident that was a 7. So if you look the right side, it's all green. So it got all right when it was certain. When it wasn't certain, it's kind of half-half. It was really not certain. Half-half is better here because there are many options. It's not as bad as just flipping coins, but still pretty bad. So in a nutshell, we took this model, which is very used, random forests, and improved it with a probabilistic interpretation, gaining some properties on it. So my final remarks here from the beginning. Resources are growing, but we have to use the resources that are growing in terms of computation. We also have to care how much they cost, energy, and find a balance, do the best we can. We should make software open and easy to use as much as possible. This is something that we typically fail in research, at least. So sometimes we don't connect to industry because we don't make that easy for everybody to use the innovations that we are doing in the university. It's important to understand all the relations of these AI approaches. So I told you here to you today about this probabilistic circuit. It is very related to the neural network that I didn't tell about, but I mentioned many times before. And so the relations between them is something that we keep trying to improve and understand better, because it will give us even better AI approaches in the future. And I have a request to people that we have really to define what AI means, and calling everything AI is not good for us. It's not good for anybody. We have to call AI what is AI, and now I'm going to say to everybody, by doing so, you're saying, oh, but that's because you want all the big pie of AI. No, take money out of AI and put in something else. There are many other things important in life. Let's stop putting all the money in AI, and then everybody calls everything AI because we keep putting money in AI. It's not helping anybody. That's my sentence here, which is probably the most controversial of the whole talk. And with that, I thank you.
are there some questions for Cassio?
Yes, I have a question about the slides that I showed timeline of all the ideas of CNN networks in the 50s or 60s already.
Yeah, we can go there.
So, yeah, if you would go back, because I have a few remarks or comments.
I hope that my
I thought you may miss 10 years or so, and all shifted 10 years later. I thought it was, but
oh, it's a bit imprecise. It could be that it's a bit after or later.
Can you repeat the question if it's there? Sorry.
Oh, but I think the question's coming.
so for example, in the 50s, you say, well, neural nets. We all know that neural nets is quite complicated. It takes a lot of computing time. But those days, you had almost no computers and no computing power. So that increases over time. So you go further in time and you show the graph with the slope. But what I'm actually always missing is how much data do you need to be successful? Because you should add a slide telling how much data do you need. Because, and also your last remark, everybody's talking about AI, but not talking what is the amount of data that you need to be successful in AI. And I think that would help a lot in all those discussions.
Thank you for the question. So the question is that in the whole presentation I talked about how hard it is for computers to crunch the numbers, but I didn't mention how hard it is for us to get enough data to put in the computer to then crunch those numbers. So we need way more data than we used to in the past for many of those models. And on this point, I would just give that all to you. You're totally right. I only didn't put on the slide because it would be even another side to talk about. But I totally agree with you that the data is essential. So the point here that we have on these years, as computers grow, availability of data grow, and not exactly in the same moment, but similar. So right now we have way more data available. Some of this data is costly. Some others are cheap. So
data available.
yes.
We have data available.
Yes.
Some companies have. That's why we look at the Nest list. That's all data we have.
True. And so the discussion around data is a similar discussion that is there. So if you want my view on this, I don't think that at this moment, and again, very biased view, I don't think at this moment what is the bottleneck at this moment of these models, it's a stopping to be data. So use it to be data much more, and now we are getting data way cheaper than we used it to. For many applications, not for all of them. And in that, I see a strong correlations where many applications that I care a lot about, getting the data is still very hard. For instance, I really interested in healthcare, right? And as we treat patients better, we have fewer with the disease, and then you have fewer data. And this is something that is coming now. So we are going back to that point where the amount of data points is actually decreasing in some fields instead of increasing. We need ways to deal with that. I think we may need something that is not a deep neural network. In this case, that amount of data keeps decreasing, and other approaches. But this is still to be seen, I would say.
So in many cases, when I see these kind of stories, I ask, how much data do you need to be successful? And you could almost tell for every type of problem, backpropagation, all the techniques, you need 100 samples, you need 1,000 samples, 10,000. Could start working 100,000. Well, you are 5% good now. If you would bring that to the discussion of AI, a lot of companies and people will stop because they will never get the data.
Very good point. So the next remark is about we should be talking more about the data, because the data has a cost for the companies, and when you start maybe a project, you don't realize that it will cost a lot to get certain data, and this was not upfront told you, and then maybe you would not even start that. I do agree with that. I don't have a solution besides saying we should be doing that way more openly. The situation is the following, in my opinion. And again, I will give another very strong opinion that people may come and disagree. I think we always need a lot of data, much more than the data we have, if you really want to do a good job. But we are just happy with the data that we are using in some sense and trying to find the best we can with that data. And in my opinion, even with these huge data sets and how much neural nets need data, for instance, to crunch some things, it's just a demonstration on how complex these models are right now. And in my opinion, this will become, at least in the future, in the near future, a very wrong direction, because it doesn't keep scaling. You cannot keep, increasing the models, and more and more and more data. At some point, this crunches, even if and breaks down, even if because of the energy or storage or something like that. So I'm in favor of looking back and say we need smaller models that perform a little bit worse, but they are much smaller than that big one that performs maybe a little bit better, but needs so much resources in terms of data, computers, and even human power to create those complicated models, because they are not all automatic as we would like. So it takes time also in that. Thanks, and I will include on my slides a data one, because it's a very good point for the future.
So could I comment also on the data? Because I think the question is not about you should have more data. It's more about how you get the structured data or the more precise data. Because as in your slide, the next slide is already mentioned, the AIs also include the internet, and that was actually designed for structurally store the data, which is bring back from the expert systems and all the knowledge domain AI model, let's say. And also later on the Dr. Watson, even though it was not really usage right now, but then that was where the logic domain, the knowledge domain, the AI model been going on. But yeah, I have a small questions on that. It was about later on actually, so it's not about here. In your the model, the examples that you mentioned, that in the leaf side, that you are adding a distributions. And I assume that you are adding a normal distribution? Is that the distribution?
Well, in this example here, the graph suggests that.
Yeah.
But let me get back, maybe people cannot hear. So the first of your point is that we need better data, more structure, and of better quality. True. But right now, if I would say what is AI at this moment, that's not the trend, right? The trend is give me as many as you can with the quality it has, and I just want this to be crunched without thinking about. I think this will break at some point. I agree with you. So we need better data. About this model here. So the point is, do you need to have Gaussians on the leaves? Actually, we could have any distribution there. The idea of the circuit is that you can combine by multiplications and sums any distribution. Depending on what you put there, you may lose some properties. But if you put them there in a mildly nice way, you keep all the properties. So it doesn't need to be normal distributions on the leaves that you combine.
Expert domain to decide which distribution.
Yes. Yes. So the point is, but what distribution I put on the leaf? Yes, you do need an expert that's going to choose. For instance, your data is discrete, it's a count. You may choose one distribution for that case, and then your data has some property like it's a flip of a coin. Then you put a binomial. The data is you don't know anything. Usually you put a Gaussian, but that is just a standard approach for most problems.
I would say some more extra questions on that, because from the informatics theory, more closing to the leaf side, and that contains more information already. So if you can increase the depth, or the depth of the tree, and then I would say eventually will give you the perfect ideas, but then why you put the distributions stop in the middle and rather than going deeper?
Okay, very nice. So the question is, do you really need a distribution here? You could just go deeper and deeper, and at some point, you don't even need a distribution. Yes, you are spot on. So you are getting the idea of the model. The model is basically partition the space of data in smaller and smaller boxes. And at some point, the box is so small that you don't need a complicated distribution. Just having a peak on the number there is enough. So you could still say that is a Dirac distribution, it's just that number and that's it. You're totally right. But this has exactly that problem that this is going to become eventually too deep and very complex with many parameters. So it's a balance between that. Eventually, you are right, on the infinity you could do that. But we also want this to be small enough to not spend too much space and time when we want to process. And that's why the distribution there. It's an approximation of this big thing that you would keep opening and open and breaking in smaller and smaller pieces. Yes?
Yes, if you say not all AI is used for anything else beyond where we go now, what were your expectations to what's useful for this world and beyond this AI?
Yeah, so I think let me put on this here, so maybe to criticize myself. So the question is AI useful for particular things more or less? What I think about where we should, let's say, maybe put more effort on AI or call AI and what we should not? I don't know if this is the direction, the question.
In that direction, but it's about your opinion. What could be more useful or a possibility to expand more?
Yeah, so the question is, I think, where is the best place for us to put our money? That is going to be the best place for AI. And I think you are asking a question that is very valuable, and I don't have the answer. But I can give some let's say, very basic educated guesses about AI. But this is really here going very crazy on my third slide where I put a disclaimer that it's just opinion. So one of the things that I believe is going to happen, okay, computers are getting better and better and models bigger and bigger, but we are still missing some key things. So those models are very, very hard to make them, to convince someone why the model is doing. By someone here, I'm going back to the explainability thing. And someone, I say, take a person from the general public at random and try to explain to this person what your AI is doing. Because that is the sort of thing we need for putting AI in many of the tasks that we have around, like in health or driving. And try to explain to that how your AI is working. And then to do that, the models cannot keep going the direction they are going. So we are putting lots of efforts on making this complicated and very sophisticated, well-performing in terms of accuracy models that we have, to explain them or to extract how they work. I'm not quite sure that this is going to go as far as we would like. It might be that we need some change on these models or something a bit different. And I do think that this may come in the next few years. So the deep learning, deep neural nets, I think they might have a cycle too. AI in the past has shown this at least, right? A few models came and died. And neural nets are quite old, and they are in a big boom right now. But I think there will be other waves, and they are not that far in the future. But all this is a very educated, biased guess of mine. And then where to apply those and where this is going to be a big thing? Yeah, I will continue here. Huh? He already started on putting me here on the spot. Let me position myself on the spot. I don't believe we can have like this self-driving cars unless it's not just AI. It's way more physical. Like we have queues everywhere and blocked things. Like as we can do for trains, right? So you put tunnels and it's very well defined the problem, then you can do self-driving. The way that is right now, well, let's not keep expecting that Tesla is coming with a self-driving soon, because that's not the case. On the other side, we are going to improve a lot on healthcare with AI. I'm not saying AI doing necessary operations, but our use of AI is still quite limited in healthcare. And so this is going to improve a lot in diagnosis or prognosis of many things. So you can see this on protein folding even, right? So those are problems that even if you make a mistake, the human can correct. So then if you look to the future, I feel that there is this combination of AI with humans that is the future. So people are calling, well, many people, myself, it's kind of an augmented intelligence. It's not like artificial. And then there is a talk by Eric Horvitz on the conference we organized in the middle of the year, which is about this, this play between humans and the AI in this case is helping when the humans can't, and humans is helping when the AI can't. So maybe this is the future.
All right. So if I understand it right, both things, human and machine learning, are still needed to make it work.
So are humans still needed to make it work? Or can we have fully autonomous AI? And my answer to that is that to have a fully autonomous, we will need something way bigger than faster computers. And that's because there are many theoretical results that are still there blocking us to continue. We keep pretending they're not there, but they are there. So fully autonomous? No. Unless there is a big boom on changing the way we do computing. Otherwise, it's not coming there. So we will need humans to do, even if a small part, we will need.
Okay. And quantum computers, does it make sense if it's faster and...
True. Quantum computers are going to help us a lot. Doesn't solve this theoretical barrier. It just makes it even more approachable, but it doesn't break the barrier.
Thank you.
Oh, you had?
Yeah, but probably you already answered. My question was, what is the biggest barrier that prevents us from adopting this all this technology to the world?
Yeah. So.
What do you consider?
What is the most valuable thing right now to make this give a big next step, right? We are doing important steps now, but I think the big step we sort of did already, and now we are extracting everything, doing small steps, in my opinion. But what is the next big one? I would say that is this, in one of the slides I talked about causality. I think this is the next big step. Causality is our ability to explain the world using a mathematical model where the relations there are really strong. So there is this idea of causal effect. All these networks that we use and many of these AI models, they are purely based on this idea of correlation between things. But you don't know what caused what. And the causality, something is coming. This is going to be, I think, a next big boom and is already showing up in research. I think it will come beyond that, but it's a big guess from my side. I might be very wrong on that.
You did mention reinforced learning.
Reinforcement learning?
Yeah.
Reinforcement learning, so the question is, what about reinforcement learning?
Because it's a complete different...
Yes, so from the, let's say, I think this kind of like goes deeper in a certain direction because I wouldn't say that reinforcement learning is a change of paradigm respect to the discussion. It's a more complicated problem to be solved. Ideas on reinforcement learning are quite smart, but most of them are from 30, 40 years ago and not from now. What is happening in reinforcement learning is that we became way more efficient to do some of those steps. So the overall idea of reinforcement learning is changing, but when we look there, it's because we are way more efficient on doing things that we already had ideas on how to do, but we couldn't. So in that sense, it fits similar with the neural nets.
I thought it was quite recent.
Well, so the question is, but I thought there was things happening more recently. Yes, so there are changes in reinforcement learning that are bigger than...
Stuff and so on.
True, but the idea behind is not that, for instance, there are ideas on searching on the tree in a way smarter way. So I'm not trying to minimize the advances that we are making. Maybe that's a wrong message. We are making lots of very cool, we are figuring out very cool things that we can do and improving on that with the tools that we have now. Most of the overall ideas that were behind, they were there on the 56s. It's impressive. Even the things behind reinforcement learning.
All right, if there's no more questions, then I'm going to come to the front. So, thank you, Cassio, for answering the questions and the great talk, and also you guys for coming up with all your comments and questions. Also, the people at home for watching and following us. So, for now, the talk has ended. I want to invite all of you to come to the bar, have a drink. Of course, the people at home can't join us, but we hope that you will join us live another time. So thanks for watching, and see you next week, and everyone here, see you at the bar. So